Hey Algebra 1 friends, here we are working on operations with radical expressions. And what you're going to find is that radical expressions are a lot like variables. So um, when I do these problems, sometimes I actually, let me get my proper pen, I sometimes literally go, oh, well, this is kind of like an X, and this is like an X, and this is like an X. And I would treat this like joining like terms together. So in this example, let's say I'm calling the square root of 5y and I call the square root of 7z, I'd have a situation like this where I'm going to join like terms together based on the similar radical value that it has or the similar radical portion of their numerical values. Blah, lots of words. So in this case, what I'm realizing is that these guys, all three of them, are like terms. So if I were to add 4x plus 6x minus 5x, I'd get 10x minus 5x, which would be 5x. So since this is an analogy, so I'm not going to write 5x as my answer is 5 root 3 though, because I have 5 root 3's. Again, I've got 4 root 3's, and then somebody comes over and says, hey, here's 6 more root 3's you can have, and then somebody says, yo, can I borrow 5 root 3's? Then altogether, I'd have 5 root 3 left. Same thing here. 12 root 5, I've got 12 root 5's, and I've got 3 root 7's, and I've got 6 root 7's, and somebody comes and says, hey, let me borrow 8 root 5's, or let me have 8 root 5's. It's not going to affect my root 7's. It's going to only affect my root 5's, or my y terms in a sense. And so with that in mind, I end up with 12 minus 8 gives me 4 root 5, right? And then everything else stays the same. So if I have 3 root 7's and 6 root 7's, really altogether, I've got 9 root 7's. And so that's how you simplify radical expressions. You just join them together and you treat them almost like they're variables. Over here, this is a little weird because they're all unlike, but what we need to do is to simplify the expression as best as we can. So here, remember what we did in the last section. We look for a number that we can divide evenly into the square root into 20. That's going to be a perfect square. And in my mind, that's 4. 4 times 5 is 20, so I can rewrite it like that. 2 times, well, what's the square root of 4? 2. So 2 times the square root of 5 is going to give me 4 root 5. So this is that. I want you to look at it, make sure you understand the process of how we did it. Just a little bit of review from the last section. Here we go again. I'm going to write this as the product of two numbers, one of which hopefully is a perfect square. And that number is 9, right? 9 times 5. 9 is a perfect square. So I can take the square root of that, and I would get 3. This would be 3 times the square root of 5. So I get 9 root 5. Notice we started off with different radical expressions, but you'd realize I can find some commonality in them sometimes. Let's do this next one, 180. Well, I know 9 goes in there evenly. So what's that, 9 times 20? So 9 times 20 is 180, but 20 we just did. We saw it was 4 times 5. So technically I can do 9 times 4 times 5, right? And if that's the case, I could have done 36, right? Do you see that 36 here? 9 times 4 is 36. Square root of 36 would be 6. Or I could think the square root of 9 is 3 and the square root of 4 is 2, and I get 6. Either way, I get 6 on the outside. I'm going to take a little extra step. 3 times 2 times the square root of 5 gives me 6 root 5. And so now I have my like terms. And there's my like terms. I have 9 plus 4 plus 6 because they're all dealing with root 5s. 9 plus 4 plus 6 is going to be 19. And 19 root 5 is my final answer. Notice we simplified each as best we could, and it just so happened that they all ended up being the same type of term. All right? We could join them together. Okay, find the area, of this rectangle in simplest form. We know the area of a rectangle is equal to base times height. And so the base has this value, and the height apparently has this value. So, golly geez, what are we supposed to do? So base is going to be 4 root 5 minus 2 root 3. And the height is going to be 3 root 6 minus root 10. Now, we can't simplify this inside of each parentheses, but what we can do is multiply stuff like this, and we know how to do it. we use the FOIL method. When we have to multiply expressions together, we use the FOIL method or the superior distributive property method. I call it super distributive. So what I'm going to do is I'm going to do just like I would if this were like x minus 3 and x plus 4. I'm going to multiply x, or this term times this term, and this term times this term. Then I'm going to take this second term, and I'm going to multiply this thing times that, and this same thing times that. I'm going to get 4 terms. I'm going to try to simplify it, do my thing, and then I'm going to get the area, or at least an expression for this area. So 4 root 5 times 3 root 6 is going to be 12, 4 times 3, root 30. 12 root 30. Then 4 root 5 times negative root 10 is going to be a minus 4 root 50. Okay? So I'm going to color code this so it makes a little bit of sense. And so the next one that I'll do is I'll multiply this negative 2 root 3 times this 3 root 6. When I do that, I get negative 6 times the square root of 18. And then finally, let's grab one last pen here. Let's do this one. I'm going to go from negative 2 root 3 times a negative root 10. And when I do that, I get a positive 2 root 30. And let's highlight that the way we did the last ones. So if you need to, take a minute, pause it, make sure that kind of makes sense where we got those values from, how we FOILed it, or extended distributive property it. It's kind of hard to say. FOIL is easier, but whatever to say, but whatever. All right, so I'm going to simplify this. I'm going to deal with the radical situation here. 12 times the square root of 30. Is there any perfect squared value that divides evenly into 30? And I'm thinking 1, that's everything, 4, 9, 16. After I get to 16, I know no other number is going to work. 16 is more than half. So I'm kind of done with this. This has to stay as 12 root 30. Let's check this one out. I know that I can break this down as 4 times the square root of 25 times 2, right? And since 25 is a perfect square, this 4 times the square root of 25 is really 4 times 5, and then times the square root of 2. So this becomes 4 times 5, remember that's a 5, this becomes 20 root 2, because that 2 cannot come out to play, not a perfect square. Let's go ahead and deal with this next one. So 18 can be broken down as 9 times 2. So what that means is I have 6 times the square root of 9 times 2, or 6 times the square root of 9, which is 3 times the square root of 2. So 6 times 3 is 18, and the square root of 2 has to stay indoors. Let's do this last one. Oh, nothing to do. We already dealt with the square root of 30, and we realized we couldn't simplify it. But hey, look at the cool thing that happens. We end up having some like terms. Whoop, whoop. So now I'm going to join my like terms together. 14 root 30. And then these guys are going to come together. Minus 20, oh, sorry about that. Minus 38 root 2. And that's it. That's the best I can do. Remember, it's like saying, hey guys, I've got 14 square root of 30s over here. And somebody says, hey, I got negative 38 square root of 2s. You can't join them together. They're two very different things. And on that, we've got some extra practice problems. If you guys want to do it, you could let me know and I'll make a video for that. But otherwise, if you're feeling comfortable, go ahead and try the assignment associated with section 11 too. Let me know if there's some way that I can help if you have some questions. Take care.